Magnetic force and field. The most popular legend accounting for the discovery of magnets is that of an elderly shepherd named Magnus. Legend has it that 4,000 years ago he was herding his sheep in an area of northern Greece called Magnesia. Suddenly, both the nails in his shoes and the metal tip of his staff became firmly stuck to the large black rock on which he was standing. To find the source of attraction, he dug up the ground to find lodestones, where lode means lead or attract. Lodestones contain magnetite, a natural magnetic material, which he didn't know at the time, of course, and it's iron 3 oxygen here. This type of rock was later named magnetite, either after Magnesia or Magnus himself. And this is a more current picture, well, because they didn't have cameras then, and also they did not have paper clips. Magnetism is a class of physical phenomena that includes forces exerted by magnets on other magnets and magnets on magnetic material. It has its origin in electric currents. And just like the electric force, it acts at a distance. It is a field force. Objects don't have to be touching each other to feel the force. A permanent magnet is an object made from a material that is magnetized and has its own persistent magnetic field. It does not go away. These include iron, nickel, cobalt, and some alloys of rare earth metals. That's it. And some naturally occurring minerals such as lodestone. Temporary magnets act like permanent magnets when they are within a strong magnetic field. So these paper clips here are temporary magnets. Let's say there's a strong magnetic field being supplied by a permanent magnet here. When they're within the field, the paper clips act like magnets. However, they lose their magnetism if we were to take away the source of the magnetic field. Paper clips, iron nails, and other similar items are examples of temporary magnets. One more type of magnet, electromagnets. Magnetism and electricity are very closely related. If you pass an electric current through a coil of wire surrounding a soft metal core, the core acts like a magnet. These are called electromagnets, and we've kind of put together the words electricity and magnetism in one word. And they lose their magnetic properties when the current stops. Magnetic poles. Just as there are two types of electric charges, we have positive and negative, there are two ways to describe magnetism, north and south poles. Unlike electric charges, which can exist by themselves, you need to have a north pole together with the south pole. You will never find one on their own. The magnetic field actually starts with individual atoms, where each atom has a north and a south pole. Magnets have two ends, which are called poles, called north and south. Like poles repel, unlike poles attract. This attraction or repulsion is the magnetic force, very similar to electric force. And here's a cool video on magnetic levitation. The compass is an indicator of Earth's magnetic field or any other nearby magnetic field. It has a magnetized needle that is free to swing about a little pivot point here. The compass needle is attracted to Earth's magnetic poles. The red part of the needle is the north pole of this little sliver of metal. Now, the red part of the compass is always pointing north. But we just said that's a north pole, so how can that point north? Well, the Earth's geographic North Pole, which is north of Canada in the Western Hemisphere, and in the Arctic, okay, that's actually a magnetic South Pole. So your North Pole of the magnet will point to Earth's magnetic South Pole, which is Earth's geographic North Pole. And Earth's geographic South Pole, which is down below Africa and South America, is actually a magnetic North Pole. So here's what we just said. A compass's true North Pole is attracted to Earth's geographic North Pole, which is the magnetic South Pole. The magnetic field is a field force just like the electric field, and we can visualize it by placing a test material that will line up with the field lines. The test material in this picture are small iron filings, and you can kind of see how they're lining up like that. Forces around magnets can be visualized by drawing magnetic field lines based on the physical picture of the previous slide. So here you go. This shows what the filings were doing. And what also happens is it goes right through the magnet. There's magnetic fields within the magnet, so the filings also line up above the magnet. The lines indicate the strength and direction of the magnetic field. The field strength and the force on other magnetized objects decreases as you get farther away, just like electric force and field. 3 magnetic field line rules. Lines exit north poles and enter south poles. They're continuous lines there. Unlike electric field lines where you could leave, if you had a positive charge here, the line would go out to infinity. Here, it loops around and goes back through the south pole. And because we don't have an infinite sheet of paper, some of these like this would go off the page and come back. But the key thing, exit north poles, enter south poles in a continuous line. The lines, just like electric field lines, never cross. And just like electric field lines, lines that are closer together represent stronger fields. So here's the strongest field right here due to that magnet on either side. Then it gets weaker farther away. Compare the electric field lines on our top row here with the magnetic field lines. Very similar, aren't they? The only difference is, let's look at this positive charge. Do you ever see any lines coming back? No, they're always leaving. And the same thing would be true for the North Pole, but if you look at the magnet as a whole, here's the South Pole, the field lines come back. So they go in big, they're not circles, but ovals, some kind of circular oval shape. Where for the electric field, this line, that can go out to infinity. Here we have, unlike poles, we have a north and a south. Here's the field lines we draw, and here's what it would look like if we had 2 bar magnets and then a bunch of metal filings thrown between them. You can see how they line up, pretty much how we drew them. And now we have 2 like poles facing each other. And look how the iron filings line up to duplicate that. Now the only thing this picture doesn't tell us is the direction of the field. Okay, that's what we put on over here based on our convention that field lines leave the North Pole. Instead of iron filings to visualize the field, a compass acting as a test magnet can be used. So here we have several compasses, 3 on each side, and the needle will swing to line up with the direction of the magnetic field around a magnet. So it would come out here, this guy would, and then come all the way back. Remember, we have to go in complete loops. Over here, see how it's following the, where it's pointed, the red comes here, over to here. See how the red's pointing back to the magnet? So let me put the arrows on here. And we'll draw one more coming down here. Red points in the direction. Come back. This points in the direction again and takes us back home to the magnet. The red side of the compass needle points in the direction of the magnetic field. As mentioned earlier, when an electric current is passed through a coil of wire surrounding a soft metal core, the core acts as a magnet, an electromagnet. Magnets can also be created by 2 other methods, induction and stroking. Induction. When a magnet is placed near or touching an iron material, the iron acts as a temporary magnet. When the original magnet is removed, the iron loses its magnetic properties. So here we have the beginning. We have a nail and some pins at the bottom, and none of the pins are jumping up to the nail. But if you touch it or put a magnet nearby the top here, some of the pins go up due to the magnetic force. Then when you take the magnet away, any of the pins that went up come right back down. A bar of steel, iron, or cobalt can be magnetized by stroking a permanent magnet the length of the metal bar several times in the same direction. This is a temporary effect wearing off over time. 1 or 2 permanent magnets can be used as shown. So we'll take the first picture here. We align the south pole of your permanent magnet and stroke it from the south to the North Pole in this direction here. And what is that? That's counterclockwise. And you do that several times, and the steel bar will join a North Pole here and a South Pole here. Or we can use 2 magnets. Take the North Pole of this magnet, go in a clockwise direction, take the South Pole of this magnet and go counterclockwise. And then you'll have a temporary magnet with the south pole here and the north pole over there. A magnet can be demagnetized by hammering it multiple times or by heating it to high temperatures. In both cases, the alignment of the atoms within the metal that produce the magnetic field is disturbed. When the field is disturbed enough, the metal no longer acts as a magnet. This can produce a permanent demagnetization.